Yes.
Yeah. Anyhow, we're very pleased to have Michael Damron from Princeton. He's going to tell us about ground states for 2D Edwards-Anderson spin glasses.
Thank you. First, I want to thank Tom for inviting me to talk about this. So this is joint work with Louis-Pierre Argan, Chuck Newman, and Dan Stein, all of whom are at Courant. And I didn't write down the references for this talk, but
it's on the archive, I guess, isn't it?
Yeah, so on archive. Also, it'll be in the next issue of CMP. It's title similar to this, Uniqueness of Ground States for Short-Range Spin Glasses in the Half-Plane. So that gives you a little bit of idea of what's coming. So what I'll first do is talk about the model in general and zero temperature ground states. And what is known about ground states? There's very little known. And then I'll specialize to the case of d equals 2. And we'll talk about certain types of ground states, and the ones that we'll be discussing, which are the so-called observable ground states, and the metastate, which is a measure on such ground states. Then we'll talk about previous results by Newman and Stein in the full plane, 2 dimensions, about uniqueness of ground states sampled from this metastate. There are partial results there, which we ended up using in our proof of uniqueness in the half-plane. So I'll finish by describing that theorem and the idea of the proof. Okay. Well, what's the Edwards-Anderson model? It's just like the Ising model, except for we have random couplings. The JXYs are taken from some IID product measure. And we generally use Gaussian or some measure which has support equal to the whole real line with no gaps, say, and which has continuous distribution. So, for example, we could put heavy-tailed couplings. That would be okay. So we form the Ising Hamiltonian with our random couplings down here, just like always, and define the Gibbs measure. So like I said, we're going to be talking about zero temperature. So, so we take beta to infinity. And as always, this Gibbs measure becomes supported on the least energy spin configurations in a finite volume. So this is all just for a finite volume. And because of the fact that the J, X, Y's are continuously distributed, you'll see that we have to have a unique minimizer of this Hamiltonian with probability 1. So what we see is as beta goes to infinity, this measure becomes a delta mass on just the ground state spin configuration in the finite volume lambda. So we want to extend this to infinite volume. But in infinite volume, of course, the energy doesn't make sense, so we have to make sense of energy differences between states. So the definition that we'll take, we'll consider some fixed coupling distribution, or coupling configuration J, and we'll say that alpha is an infinite volume ground state if whenever we try to flip any finite set of spins in that state, it costs us energy. So another way to say that is that if you look at the dual loop, which encloses the set of spins that you want to flip, this has positive energy in this sense. So this sum of all couplings, or all edges xy, which are in the boundary of this set, of this quantity jxy, alpha x, alpha y, is positive. So this quantity, the energy of this dual loop, is 1/2 of the energy that you need to flip these spins in that state.
So it would be the sum of the j, x, y's around that dotted curve, right?
That's right. Also multiplied by the spin values. So you would take plus 1 times whatever this is times minus 1.
Oh, I thought it would be across the...
Oh, I'm sorry. You're right. Yeah, so plus 1 times minus 1 times whatever j value is here.
Yeah.
And then continue all the way around.
You just sum that up.
Yep. And we'd like that to be positive. And if that's positive for all finite dual loops, then we'll call this a ground state. So it's clear that because of this property, the fact that every dual loop has positive energy, because of this is invariant under flipping all spins to their negatives, it implies that ground states come in pairs. So we have one ground state spin configuration, then its global flip is also ground state. So we'll talk instead about ground states, we'll talk about ground state pairs, GSPs.
And so you don't have any field here.
That's right.
Yeah. And is it important for you that the JIJs, if you're using it, be symmetric or not?
I don't think so. I'm not sure. I would have to go through a bunch of arguments, but it at first doesn't seem like it.
Can you reshow the previous slide for a second?
Yeah, so this is our definition of ground state pairs, and this is what we want to analyze for a fixed coupling realization J. So what is known? In one dimension, of course, like is usually the case, the situation is trivial. If we put down a set of couplings, I haven't put their magnitudes, I've just put plus or minus for their values, then once we've done that, we can choose a spin configuration that satisfies all of the edges. So that is that, we choose plus to be here, say, and then we would like to unsatisfy this bond because there's a negative coupling. So we put the opposite spin here, negative. Then we'd like to satisfy this, so we put the same spin here. We put a negative. And so if you go through the definition of ground state pair, if you try to flip any finite region, well, let's say you want to flip these three spins. Well, the boundary of that set is this edge and this edge. If you compute the energy of that, you'll get positive, because the energy, as we defined it, of each of these two bonds is positive, because everything is satisfied. So in 1D, it's very simple. You can that is one ground state, and you can show it's the only one. It's not very difficult.
And what if you do strips and stuff like that? Does that become any more complicated, or is that?
A finite height,
Yeah.
then no. If we're using Gaussian couplings, then there will still be a unique ground state. If you started to make it grow, that may be a little different. But if the couplings are not of bounded support for the distribution, then I think it's still true, but a little bit less trivial. So one dimension, things are very easy. We know how many ground states there are, or GSPs. That's the main question. So for almost every coupling realization, we have a unique GSP. So for dimensions bigger than 1, well, if we look even bigger than or equal to 3, there's really nothing that's known. And there are competing conjectures about what should be true and what is true. I don't know anything about that. What we've studied is the case d equals 2. So
would the Parisi picture say that has many ground states? Is
that's
correct interpretation?
Maybe.
It's not clear. I think at one point I thought that this would not be the correct interpretation, but Chuck reports that Parisi thinks that it would be.
Right. As far as I can understand, it seems like yes.
So there would be many ground states.
That's the prediction, yeah, by Parisi. But for d equals 2, most people believe that there should be a unique ground state, although there is a little bit of evidence that suggests there may not be. But I'll be talking today about this case.
So in any finite box has a unique ground state.
That's right.
So but when you take the thermodynamic limit, you may have.
Yeah, that's true, because our definition of ground state is just some property of spin configurations. It's that every finite set of spins you want to flip costs you energy. could be that many things satisfy that. But in a finite volume, you can show, yeah, there's just one. So that's something good to mention, that property coincides with the definition of ground state in a finite volume, which is the least energy state. So first,
What could go wrong? I mean, if it's a finite, if it's a unique ground state in a finite volume.
well, if you take bigger and bigger volumes, it could be that your ground state changes a lot. And then say you have two different limits for your ground states. For example, that could happen. And in some sense, that sort of has to happen if you have more than one ground state, in a sense.
So I have another question. I shouldn't bother you, but you look at the ground state. You look at it for a particular configuration.
Yep.
For a particular set of J's. Let's say I just do this in finite volume. Then do people worry about the sensitivity of that ground state to a small change in the,
Yeah.
in the local change in the J?
Certainly. This is one of the main plans of attack to analyze these things, is to see what happens when you change these couplings. And we'll actually use that a bunch here. I won't talk extremely rigorously about it, but I'll give the idea of some of the arguments. So we have a result by Newman and Stein that I'll talk about, which says that if there are multiple ground state pairs in 2D, and they have to be observable in this sense that I'll talk about. It means that they're in the support of the metastate measure. Then if you look at the difference between the two, the difference has to have a very strange structure. We'll talk all about what that is. So it suggests that there actually should be just one. Because if there are two, then strange things happen. And the second thing I'll talk about is this result that, in the same sense that I said before, which I haven't explained yet, there's only one observable ground state pair in the half plane. So those two things give a lot of evidence to say that in d equals 2, there's probably a unique ground state.
So you think the half-plane result is a technical result in the sense that it's probably true in the half-plane too? It's just that
Yeah.
don't have to-
That's right. Okay. So next we'll talk about observable ground state pairs. So first of all, if I get any ground state pair that just satisfies this loop condition, then I can produce it as a limit of finite volume ground states, just using the DLR equations. That I just take my ground state pair, and I take some finite box, and I take whatever spins were in that ground state pair and put them on the boundary of this box. Then what's inside will be that ground state pair. So if I use as my boundary conditions for a set of boxes the state itself, the spin configuration itself, then I will see in the limit that spin configuration as the ground state. But in order to do this, clearly I have to take boundary conditions which depend on my coupling realization. So I give you coupling realization, then you hand me a ground state, then I can build up my boundary conditions. So we'd rather have something that's more natural than that and take boundary conditions which don't depend on the realization of the couplings. So we'll say that a ground state pair is observable if we can realize it as a limit of finite volume ground states when we use boundary conditions that don't depend on the couplings. So say periodic or free or plus or minus. Those are some examples. So we're going to be looking at observable ground state pairs. And there are two reasons, basically. One is that they seem to be more physically reasonable or relevant. The second thing is that we can build a nice measure to use using these states. So this is just recap of the definition. Observable ground state pair satisfies local flip condition like all ground states do, but it's produced using coupling independent boundary conditions on a sequence of volumes.
But the result about uniqueness in half space refers to all the ground states, right?
It refers to the support of the metastate measure. So the metastate measure is supported on observable ground states. So we take a specific type of boundary condition for the half-plane result.
So you have to look at limits which are sequences which are obtained with JIJ independent
Of the boundary condition.
boundaries, right? I mean,
Yeah.
you can fix any one, but you look at all those sequences, and then
That's
the
right.
statement is that in that there's only
Yeah. So for our theorem, we will take a certain type of boundary condition. We'll take periodic boundary conditions on two sides of the box and free on the other two, and then show that the joint distribution of ground states and couplings has a limit whose measure is supported on a unique observable ground state. So in a sense, it's a natural measure to look at. It's what you see in boxes. So we'd like to look at these ground states. One thing that we could do is fix our coupling realization J and then look at the distribution of the ground state in different boxes. So say the empirical distribution. We could take a subsequence so that these ground states converge. And that would be a subsequence which depends on J as well. We'd rather not take a subsequence which also depends on J. So what we'll do is, that's not written here. Yeah, okay, well, we would rather take a J independent subsequence. The way that we'll do this is we'll consider the joint distribution in some volume of the couplings and the ground state.
what's that delta alpha?
So this is the delta mass which gives weight 1 to the ground state alpha J. So what you do is you first put down your couplings. You look in your box.
Oh, so the n refers to the size of the box? Or
Yeah.
Oh, okay. Is that right?
Yeah, that's right. Yeah, so this is a joint distribution of all the couplings, and in your box, what is the ground state? So when you sample from this, you get couplings and a ground state. So by compactness, we can extract a convergent subsequence of these measures. And this subsequence of n's will not depend on J. It'll just be, we've already incorporated the J into the measure. So the subsequence that we'll take will not depend on J. So we look at any
But you're going through periodic boundary conditions, or?
So this is in general, just for any boundary conditions you want. But later on, we'll take either periodic boundary conditions or this type that I mentioned before. So here we're taking a joint distribution of couplings and the ground state in a box. We look at those measures, and we take a convergent subsequence. So any limit point of these is going to be called a metastate. And we look at the distribution condition on J. This is supported on infinite volume ground state pairs. So once you condition on J, when you sample from kappa J, it's sort of telling you what does a ground state pair look like in a very large box with these couplings J. So like I said before, it's nice because first, it's supported on the ground states that we care about. And second, if we use periodic boundary conditions to build this metastate, then what we get is something that's translation invariant. And that's going to be very helpful for us. And it's also a natural measure on ground state pairs. You look at the joint distribution of couplings and the ground state in volumes and take a subsequence. So we want to understand what do the ground states look like that are in the support of this metastate. So the idea here will be to consider possibly two different subsequential limits for these metastates. Sample a ground state from one, sample a ground state from another, and compare the two and see how do they differ. If it's the case that when we compare ground states sampled from kappa J and from another metastate kappa J prime, if it's the case that we don't see they're any different, then it tells us that not only are these guys supported on one ground state, but they're the same measure. So that's the idea. We take two different, possibly different of these measures, and we sample ground states from each one and compare them. We'd like to show that they're not different. That's the idea. Okay, so this leads us to things that are not as confusingly abstract. To just look at two ground state pairs and look at the difference. What is the structure of this? So to do this, we're going to define the interface between two ground states. So we take some coupling realization. Let's say that this coupling here is plus, this coupling here is also plus, this coupling is minus, this coupling is plus, and put down some ground state. Then we'll call a bond unsatisfied if the product is negative of both the spins and the coupling magnitude, or the sign. So that means that the coupling is not satisfied. It's not doing what, the spins are not doing what the coupling wants. So what we'll do is look at the set of all unsatisfied couplings for, wait, let me see. Yeah, so we want to consider all of the couplings which are satisfied in one ground state but not satisfied in the other. And
those are edges you're going to look at.
yeah, these will be dual edges. Yeah. So another way to define this is just look at two ground states here, and you look at the regions where they agree, and you look at the regions where they disagree, and you put dual paths around those. So here, I've done it for us. We have agree, say at this spin, but then here we have disagree, agree, disagree.
No, I'm not sure I understand this picture. So you got two ground states there, and now how do I put this line in?
So now I look at all of the spins for both of them.
Yes.
I mark when the spins are the same. Those are agree spins. When the spins are different, they're disagree spins. So that breaks all the spins into two groups, agree and disagree.
But I mean, they agree with the Jij.
Oh, I'm sorry. So they agree with each other.
Oh, with each other.
Yeah.
Okay. So you're just putting contours around places where they disagree.
That's right. Yeah.
Okay.
So that's another way to
It's a little
define this
different.
interface.
Is it different from what you were talking about a minute ago, or?
Well, so it's equivalent to say that you look at dual edges which are satisfied in one but not in the other,
Okay.
in one state but not in the other. But yeah,
This is easy enough. You just put lines around where they don't
Yeah.
agree.
yeah. So I tend to think of it this way. Yeah.
But supposing you had an unsatisfied edge. Let's say there was plus spin on one side, minus spin on the other. And you could flip both of them, minus plus. So they would disagree with each other, but they would still be unsatisfied.
But then so we're looking at the set of bonds which are unsatisfied in one of the states but not in the other state. So when we call two spins agree spins, we're not saying that they agree with each other.
No.
I'm saying that this is an agree spin if this one agrees with this one, these are two different states.
Okay, but I thought you were implying this was related to the question about the set of bonds that were satisfied or unsatisfied.
That's true. So for every ground state, I get a set of unsatisfied bonds, say, and I compare the set of unsatisfied bonds between two different ground states. So I look at the ones which are unsatisfied in one but not in the other.
Yeah, this definition.
This is maybe some more simple.
Well, that's why I brought my example, because it showed that you can have spins that disagree without changing the set of satisfied bonds.
So what is can you say the example again?
You have plus minus,
Right.
minus plus.
Right.
It doesn't change the state of the bond, but it does change. I would disagree.
that would be a disagreement because you have to. It's the spin and not the product.
No, they both disagrees. You don't have a contract. You're right. They both disagrees.
Anyhow, I think we can move on.
Okay. Yeah, maybe for right now we just take this definition. Okay. So the theorem by Newman and Stein is that we take we sample two different ground states. Well, I guess we'll sample them later. Just for right now, take two different ground states. Then if you look at the interface between the two of them, first it must contain no loops, and also it contains no dangling ends. The dangling ends are places where the interface just ends. Second of all, if we don't just take two arbitrary ground state pairs, we sample them from the metastate, then there can be no branching points in the interface. So this is a place where the interface comes and then branches off like this. Should have a picture like here. So here we have a loop. This would count as a dangling end. And there's several branching points here.
Those can't appear.
That's right, yeah. So what we get from that theorem is that basically the interface looks like 0 or more mutually disjoint infinite paths. Yeah. Okay, so we know already that it can't be that we have dangling ends. Why is that? Because these interfaces surround disagree regions. So okay, that's clear. So all that we need to show is that there cannot be loops in the interface between two ground state pairs, and there can't be branching points.
Excuse me, no, I missed the point. So now I see some loops here. What in this?
Yeah, so this would not be able to happen if these were two ground states.
Okay.
So here we just took arbitrary spin configurations. We could have loops. Okay, so we need to show that there can be no loops and that we can't have branching points if we sample these two ground states from the metastate. So first off, why can we not have loops? Well, suppose that we had a loop. It must have positive energy in both ground states that we're looking at. Okay. But one definition of this interface is that the satisfaction status of edges on this interface is different in the two ground states. And so each edge has the opposite energy in each ground state. That means when you sum up the energy along this loop, you get the negative in one state as what you get in the other. Well, they can't both be positive unless they're 0. But we know that can't happen because the couplings are continuous. So, the energy of the loop is different. It's a negative in alpha as it is in beta if these are two ground states. And so it would have to be 0, which is a contradiction. So we can't have any loops in our interface. Any questions on that? Okay. What about branching points? First off, notice that you can't have branching points which are of degree 3 because these interfaces separate agree from disagree regions between the two spin configurations. So it would be impossible to assign agree and disagree regions if we had a degree 3 branching point here. Okay. So if you have a branching point, you have to have a branching point of degree 4. Okay, so to try to rule this out, we use the Burden-Keene argument from percolation, which rules out the existence of multiple infinite clusters in percolation. So the idea is pretty simple, just that if we have branching points, they should occur all over the place. And they should force this interface to have a tree structure. But a tree cannot be embedded in the lattice because it grows too quickly. So we should have a contradiction. So one way of saying that is, suppose that we have an interface with a bunch of branching points. We add another branching point. inside of this box, say. When we add another branching point, we necessarily have to add a new boundary point, which the interface will touch. So it says that the number of branching points is bounded above by the number of boundary points for this box. So number of branching points is bounded by the surface area. This is because, well, none of them can intersect. For example, say there was a branching point here, we had an interface which touched here, we would get a loop. Right? So none of these can touch. They have to all touch disjoint boundary points. So we have at most surface area number of branching points. But on the other hand, if having a branching point at a certain vertex is a positive probability event, then by translation invariance, you have to actually see a positive fraction of vertices which are branching points. So in expectation, we would have at least the volume order number of branching points, but we just said it was bounded above by the surface area. That's a contradiction. So that's just the standard Burton-Keene argument, but it shows us that we have this picture, where we have possibly many disjoint infinite paths, but none of them branch. You can show, in fact, that the regions between the paths cannot themselves branch by similar argument. So it implies that all of these paths, if they exist, they lie one on top of another. So you can order them. So the main result of Newman and Stein's paper in 2001 was to show that if we have an interface between ground states, then not only do we have this picture where you can order the interfaces, but in fact there's at most one interface. So the proof of that is a rather complicated argument using translation invariance, basically. So I, in the interest of time, won't go into that right now. But the formal statement is here that if you take two possibly different metastates and you sample GSPs from them, then with probability 1, either the ground state pairs are the same, that is, they have no interface, or the interface is just one path, which has positive density in the plane. So the picture we see is something like this now. Just silly. Okay. It's either empty or we see something of positive density. Okay, so that's what we know in the full plane, that if there are multiple ground states in the support of this metastate, then their interface looks like this, or there's no interface.
It has to have
Positive density. And that's from the translation invariance. Yep. So we want to try to use this result to prove a stronger result in the half plane, namely that there cannot be an interface. So this is now I'll be talking about the half plane result. So we'll start over on the setup. Now we're going to be taking a specific boxes with specific boundary conditions. So let's take, for example, boxes sitting in the upper half plane from -n to n, raising up to 2n. And let's take periodic boundary conditions on the left and right, and free boundary conditions on the top and bottom. And now, in these boxes, we put down a coupling configuration on the entire half plane, and we look at the joint distribution of that coupling configuration and the ground state we see inside, using these boundary conditions. So we call that kappa n as before, and we take some subsequential limit of those, kappa. Now we want to use the same idea as before. If we want to understand ground states in this upper half plane, what we'll do is take two possibly different subsequential limiting measures, kappa and kappa prime, sample a ground state from each one, and look at the joint distribution of that with the couplings. So that's our measure mu here. This is couplings, and then ground state pair from kappa j, ground state pair from kappa j prime. So here's the main theorem. that if we form the kappa n's, as I said in the last slide, then those kappa n's actually converge as n goes to infinity. We could also take different types of boxes, not just minus n to n up to 2n, but something where it absorbs, the sequence absorbs up our half plane. And if we look at the limiting measure kappa and we condition on j, then that measure is supported on just one half plane ground state pair. Any questions on the statement?
So you take the sequence, so there's no subsequence, just plane converges, that's the.
Right.
And well, the second thing I'm not quite sure. What does that say again?
So it says that if you look at this limit kappa,
Yeah.
and then we condition on the couplings. So that kappa is a measure on couplings and ground state pairs.
Okay. Yes.
So condition on the couplings,
Yes.
then what you'll have is a conditional measure that's supported on one ground state pair. So there's uniqueness of the ground state in the support of the metastate.
So that curve doesn't exist in other words, right?
That's right, yeah. So practically what this means is that you fix your arbitrary, in a set of probability 1 coupling configurations, and you'll see a ground state converge in these boxes. So yeah, unfortunately it's stated in this language that's a little bit slightly dense. Yeah, but okay. So as before, we take two possibly different metastates. We sample a ground state pair from each one, look at the joint distribution of that with the couplings, and we show that the ground state interface is empty. So if we show that, then it shows first that the ground state pairs that we sampled, they were the same. But if that's true with probability 1, it means that kappa and kappa prime are the same measure. But we can take kappa to be equal to kappa prime. If we do that, then it says that the kappa is supported on one ground state pair. You can't sample multiple different ground state pairs from kappa. So this is the same plan of attack as before. Okay, so how do we want to use the full plane result? The idea will be to take the half plane result, or to take the half plane setup. We have this measure mu, and we want to construct a measure on the full plane. And we want to construct it on the full plane such that it sees multiple ground state, or multiple domain walls. And that's something that we've ruled out from before. We have that if there is an interface in the full plane in this metastate, it will be just one path. So we'd like to construct a measure which sees more than one path. So the construction is to take our half plane measure mu, and we're going to translate it down. So we translate the half plane down, and as we translate, we average. So keep.
So the translation is what? Is not. So where's the half plane? Is it?
So the half plane is here, and then we shift it down by 1. We have a shifted half plane, and then the shifted measure lives on that half plane. And then we shift it down again. That same shifted measure, shifted down 1 more, lives on that half plane. So we keep doing this and average these translates. So that's our measure mu n when we average n of them. So we can take a subsequential limit of these mu n's and call this mu tilde. When we take a subsequential limit, that subsequential limit will be invariant under vertical translations, because just by construction, that we've averaged over vertical translates. Each one of these measures, mu, is invariant under horizontal translation because we built it using periodic boundary conditions on the left and right side of the box. So what we'll get in the end is a measure mu, which is vertically and horizontally translation invariant. And it'll be a joint measure on coupling configurations and ground state pairs for the entire plane.
So in a way, you're just looking far away from the boundary, right?
Basically, yeah. Yeah, so we have some picture going on, and we take a little box, and we throw it up in the air. We look and see what's going on in that box. Yeah. But we need to construct it this way to get translation invariance.
Mm-hmm.
Okay, so even though the previous Newman-Stein theorems were stated for a specific metastate measure that's built on the full plane, in fact, all of the arguments from before go through for this measure mu tilde. And we conclude that mu tilde is supported on configurations that have either one infinite domain wall or no domain walls. So like I said before, the strategy now is we would like to get a contradiction by assuming that in the half plane there is more than one ground state, and then concluding from that this measure mu tilde is supported on configurations with multiple domain walls. If we can do that, then that'll be a contradiction. So Tom, like you said, looking at a configuration sampled from mu tilde is the same as just looking really far up the y-axis in a configuration sampled from mu. So in order to understand the ground state interfaces sampled from mu tilde, we need to understand really high up in the ground state interfaces sampled from mu. Okay. So to do that, we're going to consider a specific type of domain wall. So we'll call a domain wall tethered if it contains a dual bond which crosses the x-axis. So I've drawn the tethered domain wall here so that it crosses only once. That's because tethered domain walls cannot cross twice. If they did, suppose this crossed the x-axis again, then we would have a generalized loop in our domain wall. We would have something which comes and touches the dual x-axis or the x-axis twice, and the set of spins inside could be flipped. But it's supposed to, we could use this argument that we did earlier, which said that in the full plane there could be no loops.
But you've got some branching there. I thought you couldn't have that.
We couldn't have that in the full plane.
I see.
We could a priori have that here because we don't have translation invariance vertically. And what we used to get rid of branching points in the full plane was the Burton-Keene argument, which uses translation invariance. So we do have translation invariance, but only horizontally. And it's not good enough for us.
Well, those are branch points of order 4. The ones of order 3 were ruled out in any event, right?
Yeah, so this should not be there, right?
No, the other one.
Or that one, yeah. Yeah. Yeah, you passed. That's good. Yeah, so the first important thing is that tethered domain walls touch the x-axis one time. That's it. Also, tethered domain walls can't touch each other, because if they did, then we would have basically a tethered domain wall touching twice. So these are mutually disjoint things which spread out from the x-axis. So it's already starting to look like we have multiple domain walls. So what we'd like to see is a picture like this, where we have tons of tethered domain walls coming out of the x-axis, and at whatever density they are at height 0, they don't thin out. So they don't become less dense as you go further up. If that were the case, then if we looked very far up in a configuration, we might not even see any domain walls. So, but if they retain the same density that they have at level 0, if that's some positive density, we look very far up, then we will still see a positive density number of tethered domain walls. And so in this measure mu tilde, this will be supported on configurations with multiple domain walls, because that's what we'll see up there.
I'm confused. So I thought you couldn't have this picture. I'm sorry. I thought this picture was impossible. That you only had one. Like that picture you had before.
So in the full plane, we can only have one domain wall.
Okay.
In the half plane, we don't know.
You don't. Doesn't.
Not yet.
That's the Burton. That was the Burton-Keene.
So the argument which got rid of multiple domain walls in the full plane, I didn't show. So that was what I call the Newman-Stein theorem 2.
I see.
Yeah. And
So it doesn't apply.
That does not apply here. No. They use heavily translation invariance in the vertical direction also. Yeah, that's a good
So
point.
you have to allow this.
Yeah, yeah. Yeah, so we need to somehow get rid of this possibility. And the way we'll do it is we assume that, well, if this does happen, then when we translate our little box up in the air and create our measure mu tilde will see these things, if provided that they don't thin out.
Well, how do you know they don't thin out?
That's what we need to prove.
Okay.
Yeah. So once we prove that, then basically we'll be done.
Okay.
Because then the measure which looks from infinity up here is going to see many domain walls, and that's in contradiction with the other Newman-Stein theorem. So that's really the main goal right now, is to show these don't thin out. Okay.
In other words, they don't sort of move away and open up a big gap, right?
Yeah, yeah.
They go up the axis.
It's sort of intuitively clear that that couldn't happen, because where would they go, I guess?
Well, no, not intuitively clear to me.
Okay. Well, me neither, I guess. I guess that's why we have a proof of it, right? Okay. So that's the idea. First, we want to look at height 0 and ask how many tethered domain walls are there. Well, let's look at the event A, that the edge next to the origin, whichever edge you want, is in a tethered domain wall. Well, it has to be kind of the beginning point of a tethered domain wall, because they don't touch the x-axis twice. So look at this event A. Then we use this kind of standard lemma in basic ergodic theory, that if you have a translation invariant measure, which is our mu, it's horizontally translation invariant, and you translate some event by an amount x, which is an integer. Then you ask, what is the probability that ax either occurs for no x, you don't see this event happen at all, or you see it happen with positive density, number of x's. That is probability 1. So it's impossible to see ax occur only finitely often. That's called, I think, the Poincare recurrence theorem. But more than that, not only does it have to happen an infinite number of times, it has to happen a number of times that has positive density. So if there's positive probability that a tethered domain wall touches near 0, then you will, with positive probability, see a positive density of sites on the x-axis, which are in tethered domain walls. So in order to prove that we have a positive density of tethered domain walls at level 0, we just need to produce one of them with positive probability. So I won't go into the details really of how to do this, but this involves what you were mentioning before, Tom, of modifying couplings and seeing how stable are they to local flips. So we use a local modification argument to take the interface, whatever it looks like, and pull it over to any bond that we choose.
By making it by what? Moving
Well,
the J a little bit?
yeah, you have to carefully adjust the J's, but you can do it in such a way that you can pull the interface wherever you want. It's not clear why that's true, but
But when you do that, do you just pull a piece of the interface, or can you change the whole structure of the interface?
you could change the whole structure. But all that we're guaranteeing is that if you pick a bond, then I can make the interface go through that bond.
Okay.
That's it, with positive probability. But that's all that we want, actually, because I pick a bond on the x-axis,
I see.
and if I can make an interface go through that, then I have a tethered domain wall. So I won't go into the details of how to do that. It's slightly messy, but let me just say that it can be done. It requires an extension of this metastate concept, which allows you to make local changes to the couplings and to see what happens to the ground state when you do that. So it's not particularly well defined what happens. Let's say, for example, you were in a model where you had a plus state, something which is the plus state. Then you could modify your J. You could say, well, what does the plus state look like for the modified J's? That will be what happens when I modify the J's. But here we don't have that. We don't have a plus state or any kind of singled out state. We don't know how to relate the ground states at one configuration of J's to the ground states at another configuration. So you have to be careful about that. But it can be done. Okay, so like I said, we choose an edge to intersect the x-axis, and because we can force an interface, if there is an interface at all, we can force it to go through that bond, then we will have tethered domain walls with positive probability. So that's back to down on the x-axis here. So now we would like to show that since we have a positive density of sites at height 0 in tethered domain walls, we need to show that they don't kind of thin out as we go further up. So to do that, we're going to look at height k, some height k, and define an interval which sits up at height k from minus n to n up at height k. So that's our interval ink. And we define n and k to be the number of distinct tethered domain walls that go through that interval. Okay. So if we set k equal to 0, then we're down on height 0. And we already know that there's a positive density of tethered domain walls at height 0. So this limit here exists almost surely, and it's positive. So how can it get smaller as you go up? How could the density get smaller? Well, let's consider a box which is of height k and width 2n. And we ask, where do the tethered domain walls go if they don't leave the box through the top? If you have a tethered domain wall that starts here, it doesn't leave through the top, it has to leave through the side. Okay. Well, but if you have multiple tethered domain walls, they can't all be leaving. You can't have more than 2k of them leaving, because then they'd have to intersect somewhere. They would have to intersect at some boundary point. So this says that no matter how wide your box is, the most number of tethered domain walls which can start on the x-axis and not lead through the top is 2k. So as you take this box to be bigger and bigger and bigger, what you find is that, well, we have nnk is bigger than or equal to nn0 minus 2k. If we divide by n, then this term, so we have this inequality, nnk bigger than or equal to nn0 minus 2k. Divide by n, this term will go away, and we get nnk, the density at level k, or at least the lower density, is bigger than or equal to the density at level 0. From here, it's not too difficult just to argue to say that we can find some fixed window size, such that no matter which height we put it at, the probability to see at least 2 tethered domain walls in that box is bounded uniformly away from 0. That's basically what we want. Once we do that, then the same is true for mu tilde, since we're just translating and averaging. And mu tilde will be supported on configurations with at least 2 distinct domain walls, which is a contradiction. Any questions? So just to go over the argument again, we suppose that in the half plane, there are multiple ground state pairs. And the idea is to construct a full plane measure which is supported on interfaces which have at least 2 domain walls. That's the idea. How do we do that? Well, we translate an average and create this measure mu tilde. And mu tilde is, when we sample from mu tilde, it's like looking very far up in the configuration sampled from the half plane measure. So we'd like to show that there are many domain walls up there. We look at tethered domain walls. We show that many different tethered domain walls emerge from the x-axis and they never thin out. So from the perspective of infinity, there appears to be non-zero density of tethered domain walls, where you will see at least 2 with positive probability. And that's a contradiction. That's it.